We're now at a place where we want to dig deeper into how compounds form. Our goal in this lecture is to figure out how these atoms bond together to produce the wonderful variety of chemical compounds we find on this planet.
We know how to figure out what elements are in compounds, and we can produce empirical and molecular formula. And we know from a simple conductivity experiment that the bonding must be different for different compounds because some produce ions when dissolved in water, salts or ionic compounds, and others don't, molecular compounds. The questions we would like to answer in this lecture are, how do chemicals combine in the ratios we see in molecular formula, and what factors govern the different bonding between atoms? And we would like to address this question. What dictates the 3D arrangement of the atoms in the compounds and the shapes they prefer? Let's do a quick review of a few critical concepts that we will use in this lecture. We are sure that the valence electron structure is the critical factor that determines the reactivity and bonding that we see in compounds. Now we'll be modifying our definition of valence electrons here to simplify our bonding picture. We will look at just the valence electrons located in outer and partially filled shells. This usually means we ignore filled d and f orbitals when calculating the valence electrons. For example, we know that for iodine that the electronic structure is krypton 4d10 5s2 5p5. And it would formally have 17 valence outer electrons, but for the sake of simplifying our bonding picture, we will only consider the 7 electrons in the outer n equals 5 shell as the valence electrons, and ignore the electrons in the filled 4d orbital. We also know that there is a general desire for atoms to have electronic structures that best mimic the noble gases. Remember, everyone wants to be noble. This idea drives some atoms to have positive charges and others to lean toward negative charges. The second critical concept we want to use in our bonding picture is the idea of atomic electronegativities. Linus Pauling gave each of the elements a value that described the atom's love for electrons. Fluorine was given a value of about 4.0 and is considered the element that would desire electrons the most, trying to pull electrons to itself in the most forceful way. It wants to be neon. Now, the naturally occurring alkali metal, cesium, has an electronegativity of 0.79, making it one of the elements that desire electrons the least. If anything, it would rather give away its outer valence electron to become like xenon. These tendencies, quantified by the electronegativity values, will dictate the bonding. We talked about this briefly before, but now we can discuss the different types of bonding that are possible between atoms in earnest. First, there is ionic bonding found in salts and electrolytes. In this bonding, there is a complete transfer of electrons between the two atoms, making one a cation and the other an anion. These ions are held together by attractive forces as a result of their opposite charge. Covalent bonding, found in molecular compounds, is the sharing of electrons between two atoms, thus forming a bond, a covalent bond. There are two other prominent types of bonding you'll find in chemistry too, but we won't concentrate too much on them. Nonetheless, you should know of them. Each is very important in getting a better understanding of the kinds of properties that the matter exhibits. Metallic bonding is the attractive forces formed from an electron cloud of delocalized electrons and positively charged metal ions. Complexation is bonding in which atoms are held together by coordinate or dative covalent bonds, which are like covalent bonds to an extent, but the electrons in the bond come from just one of the atoms. The electronegativity scale gives us a numerical guide to help us determine if two atoms will form ionic, molecular covalent, or metallic bonding. We will outline a method using electronegativities that can help us identify the different bonding. First, we want to take the difference in the electronegativity values, subtracting the least electronegative atom from the most electronegative element. This difference should always be, well, a positive number. For example, let's look at a selenium and oxygen bond. The electronegativities for selenium and oxygen are 2.55 and 3.44 respectively. The difference then would be 3.44 minus 2.55, giving us 0.89. Now, if the electronegativities are the same, such as in the bonding between two of the same atoms, you can get values of 0. The second number we calculate is the average or mean of the electronegativities of these two atoms. For the selenium-oxygen example, the mean electronegativity is 3.00, which we get by adding 3.44 and 2.55 and then dividing by 2. Armed with these two values, we use a simple device called the Ketelaar Triangle, which is designed to give us a general idea of the kind of bonding we can expect between the two atom centers in question. Now, it makes sense that if we combine an atom that has an extremely low electronegativity value, such as an alkali metal, and an atom with a high electronegativity value, such as a halogen, we would expect a complete electron transfer from the metal to the nonmetal, producing ions, creating an ionic bond. Cesium fluoride would be the most extreme example of this bonding and is at the top of the triangle. Nonmetals with the very similar electronegativities would be more inclined to share electrons to form covalent bonds. And the extreme example for this bonding is the fluorine-2 molecule on the far right of the triangle. Metals with low electronegativities wouldn't mind releasing electrons into a communal electron cloud to form metallic bonds, and a cesium-cesium system would be the extreme case on the left side of the triangle. For our selenium-oxygen example, with an electronegativity difference of 0.89 and an average electronegativity of 3.00, the values land us right into the covalent bonding region of the Ketelaar diagram. The great American chemist Gilbert Newton Lewis in 1916 developed a simple, formalized model that can guide us in producing first approximations to the atomic bonding in compounds, and helped in the generation of structural pictures of these differing bonding effects between atoms. Lewis represented an atom by writing down the elemental symbol, and then he would represent each valence electron of the atom with a single dot drawn next to the symbol. Remember, we're now defining the valence electrons as though in just the outer shell. The governing principle of Lewis's model is that atoms want to be surrounded by 8 electrons, or an octet of electrons, with the exception of being for hydrogen and helium, which just require 2 electrons in their outer shell. Furthermore, the electrons pair by the Pauli principle. The easiest way to envision packing 8 electrons around a drawn atom is to envision 4 quadrants with slots for 2 electrons. When filling these slots, Lewis followed a kind of Hund's rule, first moving clockwise, placing 1 electron in each quadrant before coming back around, pairing electrons up. The following drawings demonstrate how these Lewis dot structures look for each atom of the first and second period elements on the periodic table, from hydrogen to neon. Let's put together some Lewis representations for some ionic compounds. We will look first at the molecule lithium bromide. The molecular formula based on preferred ionic charge would be LiBr. Now let's look at the two elements that are in this compound, lithium and bromine. The Lewis representation of the atoms and their respective electronegativities are drawn on the slide. The difference in their electronegativities and the mean electronegativity are 1.98 and 1.97 respectively, placing their interaction right in the middle of the ionic compound region of the Ketelaar Triangle. Let's now see how we can represent this compound as a Lewis structure. For an ionic bond, the lithium atom will give up its electron entirely to become a +1 cation with a full shell like the noble helium gas. The bromine atom has 7 valence electrons and will eagerly take the electron from the lithium atom, obtaining a full octet like krypton, creating the bromide -1 anion. The anion is enclosed in brackets. The charges, placed as superscripts on each atom, are required to complete the picture of this ionically bonded compound. Let's do one more of these types of ionic compounds. Let's take the compound Al2O3, aluminum oxide. The electronegativity difference and mean for the Al and O atoms are 1.83 and 2.525 respectively, again placing it in the ionic bonded region of the Ketelaar Triangle. The Lewis representation of the two cations is to eliminate the 3 valence electrons of the aluminum atom, creating the +3 charged ions with a full electronic shell similar to neon. The 6 electrons taken from the aluminum atoms are transferred evenly to the 3 oxygen atoms, creating 3 -2 anions, giving each oxygen atom a full octet similar to the neon noble gas. Again, notice the superscripts and the brackets. One thing I've been a bit nebulous about is the actual arrangement of the anions and cations to form a 3D shape. It is not too much of an approximation to imagine that these ions, complete with full electronic shells like noble gases, have electronic distributions similar to charged spheres. These charged spheres will pack like marbles, with the anions and the cations packed close, held tightly by their attractive forces. Shown as solid salt structures for the ionic compounds sodium chloride, calcium chloride, and aluminum oxide. Now, one thing that we can observe in these renderings is that the anions with the added electrons will have expanded probability densities and can be described as large negative spheres. In an anion, electrons added into the outer orbital shells fill a reduced positive charge from the nucleus and expand the probability densities outward about the atom. The cations are small, dense spheres due to the increased pull of the nucleus on the electrons left in the atom. These closed, packed structures for the ionic solids are beautiful periodic systems with a surprising amount of variety. Sadly, further study of these structures will have to wait. Keep taking more chemistry. In water, these structures often dissolve with the ions becoming isolated from each other, surrounded by the water molecules which can orient themselves to neutralize their charge. We'll look more carefully at the ions in solvents in a later lecture.
So far, we have looked at atoms that form ionic bonds. Now, the next lecture series will look at Lewis descriptions of covalently bonded combinations of atoms. Catch you later.